Hello, and so now we want to talk about how are earthquakes measured, and that's going to be done with a device called a seismograph. And so what you're going to have is a drum that is going to have some paper wrapped around it, okay, and then the drum is going to be like this, and then as that drum turns, the paper is going to be coming off of it. All right, then you're going to have a weight that is going to be attached to a spring, and then attached to the weight is going to be a pin. And so if an earthquake does happen, the weight is going to move up and down as the ground moves up and down. So the pen's going to move up and down, and it's going to make scribbles on that strip of paper as it moves past. So the greater the strength of the earthquake, the greater its amplitude, which means that the greater the height is going to be that the pen is going to be moving up and down on the strip. So let's take a look at what these different kinds of waves would look like. So the P waves are going to be the first ones to arrive because they are, P stands for primary, so they are the fastest kind of earthquake waves. Okay, then the next thing that's going to happen is your S waves are going to arrive because they are secondary. They're the second kinds of waves to arrive at the seismometer. And then finally, you have your different kinds of surface waves. So they're going to arrive after the S waves do. Okay, now we could graph the amount of time that it's going to take for these various waves to arrive at the seismometer versus the amount of distance. Now, normally in physics, when you graph something, you always want the time to be going sideways, and then you want the distance to be going up and down. And then the slope of that line, which is going to be rise over run, would be distance over time. And so then the slope of this line is going to be the speed. Well, you'll notice that in this picture here, it's not drawn that way. So you'll notice that in this graph, its time is going up and down, and then the distance is the one that's going sideways. Now, you can still get a slope when you do that, but this time the slope turns out to be the inverse of the speed of the earthquake wave. So this time, instead of it, the slope of this one, instead of being V, is going to be 1 over V. So then that would mean that whichever line is the steepest, that's actually going to be the slowest wave. The steepest line on this one would have been the fastest wave, and then the steepest one on this one would be the slowest wave. So if you notice on that picture there, it shows the S waves as being the ones that are the steepest, and then the P waves are a little less steep. And that's because the S waves are actually slower than what the P waves are. Well, the point is that scientists have measured the distances that different kinds of earthquake waves can travel. They've measured the amount of time it took it to do it in, and then they have graphed it on a piece of paper. So on this one, you see that one of the lines represents S waves. The next line is going to represent the S waves, and then the final one is going to be the S minus the P waves. Now that's the one that we're going to be interested in, because we can use that time delay in order to figure out how far away a particular earthquake is going to be. Okay, so for example, let's say that we measure the arrival time of some P waves, and then we measure the arrival time of some S waves. Okay, and now let's just say, for the sake of argument, that there's a minute in difference between the two. So the P waves are going to arrive first, primary waves. We click our stopwatch. 60 seconds later, the other S waves, they arrive. So on that graph, we find 60 seconds. So find 60 seconds on the up and down part. All right, now you're going to go sideways until you get to the S minus P graph, so that straight line, and then go down, and you will notice that it says 600 kilometers. So now we know how far away an earthquake has occurred by using the arrival times of these different kinds of waves. Now that still doesn't really help us, okay? So now we know that this particular earthquake, the epicenter of this earthquake was 600 kilometers away. So that would mean that if this is your seismic station, then that epicenter is anywhere on that circle. So anywhere that is 600 kilometers away. Now, if though we had a second seismometer, so let's say that there's another seismometer over here, and they measure the same earthquake, and they find that, let's say it's not 600, let's say that they said it was 500, and then you draw a circle around that. This is not a very good circle. But now notice that we've narrowed it down to the epicenter can only be two places. So the epicenter is either going to be here or it's going to be here. So what do you think we're going to need if we want to narrow it down to just one place? We're going to need 3 of these seismic stations, and then each one of them will say that the epicenter is at a different distance. We draw circles around each of the 3, and then lo and behold, where those 3 come together, that will be the actual epicenter of the earthquake. Now, it's not going to be the hypocenter, so it's not where the earthquake really occurred at, because it really occurred under the ground. But what we've just figured out is what's the source of the earthquake at the surface of the earth. So we're going to call this triangulation. Okay, let's take a break, and when we come back, we'll talk about where do we find earthquakes.